Namaste everyone, welcome to another class in current electricity. Today we will be doing what is seen on your screens. We will be discussing about one of the most important things that is needed to be considered for an electrolytic cell. That's EMF that expands to electromotive force. And what is the difference between the voltage or the potential difference that we have been hearing about all these years and what is being introduced today, that is EMF. So we are going to discuss about the differences between these two terms, and if time permits we will be moving into the behavior of cells when they are going to be grouped, because as resistance in series and parallel have been reduced from your syllabus, we will be only concentrating on series and parallel combination of cells. So these are going to be our objectives today. Let's see how far we can proceed in this. Now, in order that we are going to understand what is meant by EMF of a cell, I'm going to again go into a little bit of chemistry. In electrochemistry, when you are going to talk about a simple electrolytic cell as is seen on your screens. Now, this is a simple zinc copper cell. And in electrochemistry, you will be further doing it in detail. But before or without talking about this, I wouldn't be completely explaining about EMF to you. So here we go, an electrolytic cell. So this is not, please understand, this is not an electrolytic cell that you were introduced to in your lower classes in chemistry for some processes like electrolytic refining, where you see a single electrolytic cell and two electrodes dipped in the same electrolytic solution. But here, if you see, you have two cells, two individual cells. Basically, we call them as half cells. Okay, this is called as the oxidation half cell, and this is called as the reduction half cell. Now, how do you know which of these will undergo oxidation or reduction? Again, from your chemistry, by comparing the standard electrode potentials of these electrodes with hydrogen, that is She, which is basically having a zero electrode potential. So the relative potential in comparison will tell which will undergo preferential oxidation and which will undergo preferential reduction. So if you are going to look at this cell where I have zinc dipped in zinc sulfate and copper dipped in copper sulfate solution, zinc undergoes preferential oxidation in comparison to copper. So what happens to the zinc on this electrode? The electrode corrodes, or the metallic ions in the zinc electrode are going to move into the solution as zinc ions, as you can see over here. You see here, it moves as zinc ions, leaving the electrons on the electrode. So that makes my electrode negative in comparison to the solution. Is that clear, children? So because here zinc undergoes oxidation, this electrode is going to behave like an anode. Please understand, in electrolytic cells, again, your knowledge of an anode attracting anions and a cathode attracting cations should be erased. An anode in an electrolytic cell is that which is rich in electrons, and a cathode is that electrode which is rich in positive ions. Please get that clearly, right? So here zinc behaves as an anode because the zinc metal on the zinc surface is going to move into solution, accumulating electrons, making zinc negative. So what happens in the case of copper electrode in copper sulfate solution? The copper ions in the copper sulfate solution start depositing on the copper by taking up electrons. It's going to gain electrons, undergoing reduction. So there is going to be accumulation of copper ions on this electrode, bringing it a positive charge. So this becomes relatively positive with respect to the solution. That means that if I consider any point in the solution here, this is going to be relatively negative. And if I consider any point over here, this becomes relatively positive. Whereas the electrode, I'm sorry, yeah, that's right. So here the electrode becomes negative, and the other case, the electrode becomes positive. So if I am going to look at, now why is there a salt bridge over here? Again, your chemistry, electrochemistry, what does my salt bridge do? The salt bridge is generally sodium chloride, potassium chloride, or potassium nitrate in agar-agar. Agar-agar is again a gel which is going to, this salt bridge is going to prevent reaction between these two, the movement of these two electrolytic solutions into one another. So this basically splits up as K plus and NO3 minus. So what does this salt bridge do? It keeps your cell electrically neutral. That is, when there is going to be accumulation of Zn2 plus in the solution, nitrate ion comes into, jumps in to help in order to neutralize the excess Zn2 plus. And here when copper ions go on deposit metal, electrode, sulfate ions accumulate in the solution. So in order to neutralize the accumulation of sulfate ions, K plus jumps in to help. That is the basic idea of using a salt bridge. And all this you are doing in your chemistry, in electrochemistry. So what happens? There is a negative potential that is developed over here, and there is a positive potential that is developed over there. Now, what happens when there is a positive potential that develops over there? Now, because of this positive and negative potential between the two electrodes, there is a potential difference that exists even in the absence of the circuit being closed. So what is going to be the effective potential difference? Say, suppose if I'm going to take this point as A and this point as B, what's going to be the potential difference across these 2 points? The VAB is going to be equal to VA minus VB. Is that clear? But if I'm going to consider the zinc plate, the potential, the electrode potential is already negative. So what actually happens over here is VA minus of minus VB becomes VA plus VB. This potential difference that exists, or what is potential difference? We know it's the work done per unit charge. So this work done per unit charge is what we call as the electromotive force. Please understand, though we use the word force, it is basically the work done, right? So this work done in moving in an open circuit is what we call as electromotive force. So effectively, if I am going to connect a device that is going to measure the potential across these 2 terminals, which is definitely not a voltmeter, though I'm going to show you the next figure where if I am going to connect a voltmeter, by voltmeter I don't actually mean the voltmeter that you see in your laboratories. We are going to use a different kind of a meter which we will be doing in the forthcoming classes. If at all I'm going to measure the potential difference across these 2 terminals, that is what I'm going to call as the EMF of this cell. And what is that going to be? The EMF of this cell is going to be equal to, because if I'm going to look at the standard electrode potential of the zinc, that is the reduction, oxidation cell, that's going to be minus 0.76 volt. Whereas if I'm going to look at the reduction half, that is the copper cell, half cell, we call them as half cells. You are going to study about it, how you are going to denote a half cell in chemistry. If I'm going to look at it, the electrode potential is plus 0.34 volt. So what happens? Plus 0.34 minus of minus 0.76 volt is going to give me 1.1 volt. This is called a Daniell cell, and this cell gives us a maximum potential. We call this as the maximum potential difference across the electrodes of the cell, and this is what we call as EMF of the cell that exists in a cell. Please understand, this is because of the conversion of chemical energy into electrical energy. So even in the absence of an external load connected, there is a potential difference that exists. But please understand, the cell is still electrically neutral. So there is no flow of current under such a condition. So this is basically an open circuit condition because there is no flow of charges. The salt bridge maintains the equilibrium, the electric equilibrium in the circuit. There are no excess ions, and hence there is no flow of current. The cell is basically in open circuit condition. So this potential difference is what we call as EMF of the cell. So the potential difference between the terminals when they are not connected to an external circuit, when no current is drawn from it, is what we call as electromotive force. And as I said, this is misleading because electromotive force is basically the work done to move a unit positive charge from one terminal to another terminal. Please get this idea very clearly. EMF is going to be when the cell is in open circuit, when no current is going to flow or to be drawn from the cell, which is going to be our primary source of electricity in any given circuit. So what is going to be terminal potential difference? Let's get this very clearly. When I am going to connect an external load, let us assume this is going to be the external load with a resistance R. Now what happens? Electrons are going to flow from the anode to the cathode because the anode, which is the zinc terminal, has accumulated electrons on it. So what is going to be the direction of the conventional current? If I am going to show conventional current direction, so this is going to be the direction of the conventional current. But what actually happens between the electrolytic solutions? Please look at it carefully. Now here in this solution, I have accumulation of SO4 2 minus ions, and in this solution, I have accumulation of Zn2 plus ions. So basically what happens, as I told you, in the salt bridge, if I'm going to have KNO3, that is, let us assume if it is going to be potassium nitrate, solution. So in agar-agar, then what happens is my nitrate gets moved here. That means negative charges are flowing in this direction, while positive charges are flowing in this direction because K plus is moving in. So if I am going to consider the conventional current direction, the direction of the current in the external circuit is opposite to the direction of the current in the internal circuit. By external circuit, I mean the load that is connected, and by internal circuit, I mean the electrolytic solutions of the two half cells of your Daniel cell or your Leclanche cell, right? Now, what happens in this case is this. Because of this, because of the movement of charges, you know, whenever charges begin to move, there is a resistance that comes up in the circuit or the conductor or the electrolytic solution. So internally, there is a resistance that is going to be developed in the cell. We are going to call it, give it the symbol small r, and we are going to call it as our internal resistance of the cell. So this internal resistance of the cell, if you look at it, is since the external resistance and the internal resistance are going to be in series with each other, they are going to actually make up to the total resistance of the closed circuit, which is going to be R plus R. So please get that very clearly. The current through the load, if I'm going to consider, is from positive to negative, while if I'm going to look at the cell as such, internally, the flow of the conventional direction of the current is opposite to the direction of flow in the external circuit. Because the flow begins, because you have connected a wire, because you have given a conducting medium, the excess charges begin to flow externally and internally, giving rise to a closed circuit. Now, under this condition, if you are going to measure the potential difference across the terminals of the cell, across the electrodes of the cell, whatever is the drop is what we call as the terminal potential difference of the cell. Now, if I'm going to redraw this circuit in the form of a symbolically represented circuit diagram, you actually get something of this sort. I have a negative electrode, that's going to be my zinc. Positive electrode, that's going to be my copper. So here, if you see, the current direction is from copper electrode through the load to the zinc electrode. Please understand, this is the direction of the conventional current. Now, if you look at this dotted line structure, this is basically the cell in total. Is that clear? It is the total cell with its internal resistance, and the external resistance is going to be capital R. Now, what are we going to do? If I'm going to talk about the current in the circuit, let I be the current in the circuit, then what is going to be the the total resistance? I've already told you. So what is going to be the current in the circuit? Because the maximum potential is the EMF divided by R plus R. So if I'm going to cross multiply and rearrange my equation, E is the alphabet that I use for the EMF of the cell. So I have it to be equal to IR plus IR. Now this is the drop across the external load. Now that will be equal to the drop across the terminals, because the load is connected parallel to the electrodes. So I'm going to call that as the terminal potential difference, V plus IR. So I get my expression for the terminal potential difference to be equal to E minus IR. So you can see here the terminal potential difference is always less than the EMF, because EMF is the maximum drop when no current is taken. Now, when current begins to flow through it, there is some resistance that is acting on it. And you can also say here, you can see here that I becomes negative over here, because internally the current flows in an opposite direction, and that reduces the internal resistance, reduces the drop across the load and or the drop across the terminals of the battery, and I get V is equal to E minus IR. Hope you understood. So here what happens when I becomes a zero, that is when the system is under open circuit condition, you have V is equal to E. That means the terminal potential difference is nothing but the EMF when no current flows through the cell. So please get that very clearly. Now, if I'm going to use this expression of V is equal to E minus IR, and I'm going to try and derive an expression for the internal resistance of the cell, how am I going to get it? So I have my IR to be equal to E minus V, and I'm going to write my V as IR. Is that clear? So what am I going to do? I am going to divide throughout by, or if I am going to take up my I, divide throughout by I. So I have my E by I minus IR. Isn't that right, children? But if I am going to denote it, suppose I do not want to give it in terms of I, and I want to give it in terms of the potential difference, the terminal potential difference. What can I again do? I can divide this from here. I can divide totally by V. Say, for example, I multiply and divide this equation by R. So what am I going to get? So this becomes E by V minus I, because this IR becomes V over here. This R remains outside. So I hope you get this clearly. So if I have to express it in terms of current, if I'm going to express internal resistance in terms of current, I can use this. And if I am going to express internal resistance in terms of voltage, I can use this. So E by V minus I into R, or E by I minus IR. This is what is going to be the internal resistance offered by the cell. So please understand, this is basically two half cells, and in the laboratories you are not actually going to see a figure like this. You're not going to actually see a figure like this. You are going to see only one single container, but there you will use an earthenware material to to separate the two electrolytic solutions, which is generally a ceramic cylinder, inside which we are going to use two different electrolytes. There will be a glass container which will contain one of the solutions, and there will be a ceramic container inside it in cylindrical form, which will have another solution with two electrodes dipped in it. That's what is going to be your Daniell cell in the laboratories. So we move on to see what is the differences between electromotive force and potential difference. And most of these differences were were said during the course of this session. So you can see here that EMF is basically in open circuit, while potential difference is in closed circuit. EMF is specific for the cell. You cannot measure EMF across a resistor. You cannot measure EMF across a capacitor or an inductor, but potential difference can be measured across any 2 points in a closed circuit. It is not specific to a cell. And EMF is independent of the internal resistance or the external resistance connected in the circuit, while potential difference basically depends upon, because V is equal to IR, it is proportional to the resistance across the points where you are measuring it. And my EMF is maximum and the potential difference is always less, but when you are charging, the potential difference is, that is the battery, that will have a greater potential difference than the battery that gets charged. And of course, EMF becomes the cause and potential difference becomes the effect, because without EMF, there is no potential difference. And as we were discussing about the two half cells, we saw that EMF is because of the conversion of chemical to electrical energy, whereas potential difference is due to the difference in potential, that is the difference in work done or the fall in potential from one point to another point. So that's the difference between these two terms that are major to discuss when we are talking about a given electrical circuit or a given primary source of electricity in a circuit. Is that clear, children? So what I'm going to do is I'm going to close this session with this, and I will see you again for the last objective, that is going to be grouping of cells. So these should have been the outcomes till now. After listening to this short session, you should be in a position to define what is EMF. Not only to define EMF, you need to understand the difference between EMF and terminal potential difference, because when I'm going to use a cell in a circuit, it is basically the potential difference that we are talking about and not the EMF. EMF is going to be the maximum PD across the cell when no current is being drawn from the cell. So hope we have achieved these. If not, please, I would like you to repeat the video, watch again, or you can do a self-study on EMF of a cell from chemistry point of view, as I was talking about using oxidation half cell, reduction half cell, the standard electrode potentials of each of those cells. Why does zinc undergo preferential oxidation, while why does copper undergo preferential reduction? And all these is from the chemistry point of view you are going to study, and then you come back to understand the open circuit behavior of a cell. That will give you a very, very, very good idea. So please keep these things in mind and be ready for the next session, where we will be discussing about the grouping of cells in series or in parallel. Till then, stay safe.